Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last class, we had started to discuss about equilibrium problem when there are link interactions. Okay, so we were considering this situation where the travel time on a given link is not just only the function of the flow on that link, but it can also be a function of the flow on other links. Okay, so specifically, we were considering the case of this two-way streets here. Um, where there is one street, but then there are flow in both the directions here, and the travel time on one direction is not just dependent upon the flow in that direction, but it is also dependent upon the flow on the other direction. Okay. So, these two directions we can represent them by two separate links. So, let A dash denote the link opposite to link A. Okay. You can think that this A dash dash will then again be link A, okay, because this dash operator we are using it to denote the link which is opposite to a link A. Okay. So, the link opposite to the one which is opposite to A will be again link A only. So, we will represent the link performance function on a given link A by this TA here. So, now TA is the function of xa, which is the flow through this link A, and also it is function of xa dash, which is the flow on link which is opposite to this link A. Okay. So, previously we were just considering that TA is equal to TA xa, okay, but now this travel time is also a function of the flow through the opposite link here. Okay. And similarly, we can write down the travel time function for this opposite link here A dash. So, that will also be having this x A dash and x A in its argument, that is it will be a function of the flow through that link A dash and also the flow through the opposite link, which in this case will be link A. Okay. So, the travel time in a given direction is considered to be a function of the flow in both the directions. This travel time, however, is assumed to be independent of any other link flow in the network. Okay. So, we are assuming that the travel time on this link A is only a function of the flow through this link A and the flow through the opposite link, and no other flow on any other link in this network is affecting the travel time on this link. Okay. We will be later considering the extension where the flow through a given link A can also affect the travel time of various other links, not just the link which is opposite to this link A. Okay. So, in the case of two-way traffic, the interaction between the opposite direction links can be assumed to be symmetric. So, what do we mean by symmetric here? That is, the effect of an additional flow unit along a particular link on the travel time in the opposite direction equals the effect of an additional flow unit in the opposite direction on the travel time of the link under consideration. Okay, so this is slightly long sentence, but mathematically it is a very easy concept. It means that the rate of change of the travel time on link A with respect to the flow in the opposite direction link is the same as the rate of change of the travel time on the opposite link A dash with respect to the flow on this link A. Okay, and this holds for every pair of link A. Okay. So, here we are taking the partial derivative of the travel time on link A with respect to the flow on link A dash. So, link A dash is the link which is opposite to link A, and here you can see that the travel time of link A is a function of the flow through link A and also the flow through link A dash, and this is equal to the partial derivative of the travel time on this link A dash, which is a function of the flow on that link A dash and also the flow through the opposite link A, okay. And we are taking the partial derivative with respect to the flow on link A, okay. So, this is a very important condition that you should be aware of. So, this optimization problem can also be developed here for this case that we are considering. So, if you remember the different versions of equilibrium problems that you considered, for example, the basic version of the deterministic user equivalent problem, and then we considered the stochastic user equivalent problem. So, each of these user equivalent problems we showed that they can be formulated as equivalent optimization problems, okay. So, same can be done here also. So, this is the objective function for that equivalent optimization problem. So, here we are minimizing this function zx, where this half is getting multiplied to this sum here, and the sum is over all the links A, and then there are two terms here, there are two integrals here. One integral is having this travel time of this link A, but in the argument we are integrating with respect to the flow on this link A, and we are assuming that the flow through link A dash, that is the opposite link to link A, that is kept constant. So, that is why we have written it as x A dash, okay. So, since the integral is happening with respect to the flow on this given link x A here, so while doing this we are keeping x A dash, that is the flow on the opposite link, to be constant, and in this second term here we are keeping the flow through the opposite link to be equal to 0, okay. Now, again, as with any optimization problem for an equilibrium problem that we have seen until now, this objective function is not very intuitive. So, like we have seen the objective function in the Bachmann's transformation, we had mentioned that it is an construct that has been made to ensure that the equivalent first order conditions are the same as the user equivalent problem, okay. So, in this way the same is the case here. So, why are we writing this objective function in this way is that when we write it in this way, then the first order conditions that we develop for this optimization problem, that will become equivalent to the user equivalent conditions in this case when we have link interactions, okay. So, this was the objective function, and then we have the constraints. The constraints are exactly the same that we had seen for the user equivalent problem. So, this is the constraint that the sum of the flows on different paths connecting any OD pair RS is equal to the demand on that OD pair, and this is the condition that the path flows have to be non-negative, and this is saying that the flow through link A is the sum of the flows of different paths that are passing through it, okay. And in order to connect the link flows XA with the path flows FKRS, we have this parameter delta AKRS. We have discussed this many times before. So, delta AKRS comes from the network structure. So, this can be calculated beforehand. So, this is a given quantity, it is not a variable, okay. So, the constraints are the same as before, okay. Only the objective function is different as compared to the deterministic user equivalent case when we had no link interactions, okay. So, this is again saying that the objective function has two terms here. The first term, that is this integral which is going from 0 to x Ta omega x A dash d omega, is the integral of the link's performance function with respect to its own flow. Why we are writing own flow? Because we are doing the integral with respect to the flow on this link A when the flow in the opposite direction is held constant, okay. So, we are keeping the flow in the opposite direction to be x A dash, okay. So, x A dash is not dependent on x A. So, we are putting it as it is. And then we have the second term here. So, in this case we are putting the flow on the opposite direction to be exactly equal to 0. Okay. And we also saw that there is a half term in this objective function, and the reason for putting that is when we do that, then the scale of the results will conform to the results of the earlier version of user equilibrium. Okay, so when we will be seeing the when we will be starting the discussion towards the derivative of this objective function value, so then it will be clear that why this half is used. Okay. So, the half purpose is that whatever results we are getting in the case when there are no link interactions for the deterministic user equilibrium case, the results follow in the same trend. Okay. So, that is why we have scaled to put that half value, and as I had mentioned before, the constraints are the same as the basic user equilibrium problem. Okay. So, before we actually present the first order conditions for this optimization problem when we have the link interactions, let us first determine the derivative of this function zx with respect to the flow on a particular link. Okay. So, in order to take the derivative of this function objective function here, we need to differentiate each term here in this objective function. Okay. So, if you remember, there are two terms. In the first case, we were keeping the flow on the opposite direction to be constant, and in the second case we were keeping the flow in the opposite direction to be equal to 0. So, let us first take the derivative of the first term here. So, this is the sum here over all the links, where every term is an integral with respect to the flow of link A, and the flow on the opposite direction is kept to be constant x a dash here. Okay. So, we are taking the derivative of this sum with respect to flow on link B here. This is what we want to do here. Okay. So, we are taking derivative of this summation with respect to the flow on link B. Okay. So, when we do that, then what will happen is that there are only two links which are a function of the flow on link B. One is the link B itself, and the other is the link which will be opposite to link B. Okay. And that is why we have exactly two terms here. So, previously we had a summation which is going through all the links A in the network, but finally we end up having only two terms, because only there are two links in this network which are a function of the flow through link B. One is the link B itself, and the other is the link which is opposite to link B. Now, for the case when we are having this link B to be equal to that link A which we are considering in this sum. So, this is the first term here, and this is the case when we are having this link B dash which is opposite to link B. Okay. So, here you can see that in this case when we are considering A to be equal to B, so this integral is a function of xb here. Okay. And that is why this term is not 0 here, and similarly the travel time on the opposite link to B, which is B dash, that is a function of xb here, that is the flow through link B. Okay. And that is why this term is also not going to 0, this is something non-zero. Okay. But all the other terms in this sum, when you take the derivative with respect to the flow on link B, that will be equal to 0, and that is why we have only taken these two terms here. So, the first term in the above expression, that is this one we are talking about, can be easily evaluated by the fundamental theorem of calculus. So, this one can be easily written as this here. Okay. So, if you don't recall the fundamental theorem of calculus, I will suggest that you check any standard text on calculus. So, this term we can easily simplify it in this form. So, this is just the travel time on link B, and since it is function of the flow on link B and the flow on link opposite to link B, which is B dash, so that is why we get this. Okay. Now, the second term here, this can be evaluated by moving the derivative inside the integral. Why we can do that? Because xb is independent of xb dash. Okay, so this integral is going through the flow on link B dash, whereas we are taking the derivative with respect to the flow on link B. Okay, so since the flow on link B is not dependent on the flow on link B dash, so we can take this derivative inside the integral. Okay, so when we do that, this is equivalent to this here. So we have taken the derivative inside the integral here. So we now need to evaluate this. Okay, now what we will be doing here is that we will be using the symmetry condition that we had assumed in this case when we are considering the link interactions. Okay, so if you remember, we had assumed that the partial derivative of the travel time on link A, which is the function of the flow on link A and the flow on link A dash here, with respect to the flow on link A dash, this is equal to the partial derivative of the travel time on link A dash, which is the function of the flow on link A dash as well as the flow on the opposite link, which is link A here, with respect to the partial derivative with respect to link A, flow on link A. Okay, so we will now consider and use this equation here. Okay, so therefore this, I mean this is the same as this, and given that we use this symmetry condition that we have for the link interactions, we can write down that this is actually equal to this here. Okay, so you can see that what has changed now. See, the limits of the integral have not changed. Here it is xb dash and here also you have xb dash. But now here, instead of taking the derivative of the travel time on link B dash, we are taking the derivative of the travel time on link B, and previously we were taking derivative with respect to flow on link B, now we are taking the derivative with respect to flow on link B dash. Okay, and both these links B and B dash have travel times which are function of the flow on link B, that is why you have xb in both the cases here, and of course it is also dependent on the flow on that link B dash. Okay, that is why you have omega here. Okay. So now that we have used this symmetry condition, so this is the integral that we need to evaluate. So this integrand can be easily evaluated as a definite integral. That is, we can now take these limits here of the integral. So when we will be putting that, we will be getting one term as travel time on link B, which is a function of the flow through link B and the flow on the opposite link B dash, minus the travel time on link B when the flow on the opposite direction link is 0. Okay. So with this, we have evaluated the integrals for the first term in the objective function. So we had split that into two terms. Okay, so we will now write that together. So the derivative of the first term in the objective function with respect to the flow on link B is equal to this. So previously we had one more term. So from there we were getting TB xb comma xb dash, and then we have added that to this one. That is why we are getting 2 TB xb comma xb dash minus this. Okay, so if you remember, we had one more term other than this. Okay, so from there we were getting that derivative is equal to this. I mean this is xb and this is xb dash here, and we have added this to this. Okay, so that's why there is a 2 coming now here, and then we have this. Okay. Now we need to also evaluate the derivative of the second term in the objective function. So the second term corresponds to that one where we fix the flow on the opposite direction link to be equal to 0. Okay. So now this value is equal to this. Okay. And this again can be evaluated by the fundamental theorem of calculus. Okay. So since we had fixed, I mean, you might be wondering that why there is now only a single term here. Previously when we were doing the derivative of the first term in the objective function, we had landed up with 2 terms, and now there is only a single term. The reason behind that is, see, now here in this second term in the objective function, we anyway have the flow on link b dash, that is the link which is opposite to link b, is equal to 0. Okay. So that is why the only link which is having which is dependent upon the flow through link b is the one which is the same as link b. Okay. So that is why there is a single term here, and then with the use of the fundamental theorem of calculus we get this. So we have now evaluated the derivative of both the first term and the second term here. Okay. So we will now write this together so that we get the derivative of the overall objective function. So these are the 2 terms here that we have evaluated. So for the first term we had obtained that its derivative is 2tb, where tb is a function of xb and xb dash minus tb xb comma 0. Okay. And for this second term here we got that this is equal to tb xb comma 0. Okay. So these two cancel here, and since there is a half term here, so this 2 also gets cancelled with this one, and finally we get that the derivative of the objective function with respect to the flow on link b is equal to tb xb comma xb dash, that is, this is just the travel time function of link b. Okay. So we have written this again here. So the derivative of the objective function with respect to the flow on link b is equal to the travel time of function of link b. Now if you recall, this is in line with what we had seen when we were considering the deterministic user experience problem, but there were no link interactions. Okay. So there also the derivative of the objective function with respect to the flow on link b was equal to the travel time function of link b. Okay. Just the only difference was that at that case the travel time through any link b was only a function of the flow through that link b, and now in this case the travel time through link b is also a function of the flow through the opposite link, which is b dash here. Okay. So that is why there is x b dash also here. Okay. So this is saying the same thing, the derivative of the objective function with respect to the flow on a particular link is the travel time on that link. Okay. So this is similar to the one which is obtained when there are no flow interactions. Okay. So that is what I had said. Now given that this is actually the same result that we had obtained when we had considered link interactions. So now onwards, if we try to derive the first order conditions, the process will be the same and we will be getting the same form of first order conditions. Okay. So that is why that is not presented here, and the only target was to show that since the derivative of the objective function is coming out to be the same as it used to come out when there were no link interactions. So the first order conditions will follow in the same way. Okay. So, therefore, the first order conditions for this optimization program are as follows. So, these are the same first order conditions that we had seen before. So, here the last two are just the normal constraints that we have in the user equilibrium case, okay. That is these flows on different paths connecting an OD pair sum to the travel demand, and the path flows are non-negative, and these two are the important conditions which ensure that, for example, if the flow on any path k connecting R to S is equal to 0, then this is the only useful information that we get, that the travel time on path k connecting R to S will be greater than equal to the minimum path travel time on that OD pair RS. Okay. So, that is, if a path is not getting used, that is the flow on that path is 0. So, then the travel time on that path will be greater than or equal to the travel time on any used path, okay, connecting that same OD pair. And whereas if this FKRS is positive, that is this path k is getting used between this OD pair RS, then CKRS will be have to be equal to URS from this condition here. Okay. So, in that case, the travel time on path k connecting R to S, that is CKRS, will be equal to URS, which is the minimum path travel time between OD pair RS. Okay. So, this results into the same condition, that the travel time on all the used paths connecting any OD pair will be less than or equal to the travel time on any unused path connecting the same OD pair. Okay. So, these conditions are therefore the same as the basic user equilibrium conditions that we had seen when there were no link interactions. Okay. Now, it should be noted that these conditions hold under the assumption that the link interaction is symmetric. Okay. That is, the derivative of travel time function on link A with respect to the flow on opposite link is equal to the derivative of the travel time on opposite link with respect to the flow on the given link A. Okay. Because if you remember, when we were trying to determine the derivative of the objective function with respect to the flow on link B, then we had used this symmetry condition. Okay. So, while evaluating one of the integrals, we actually use this symmetry condition, and that is why these conditions actually hold when the symmetry condition holds. Okay. And also, these first order conditions have a unique solution under the following assumptions. So, what are those conditions here? The first assumption is that travel time on a link is a strictly increasing function of the flow on that link. Okay. So, this is not the first time we have seen this condition here. Mathematically, it means that the derivative of the travel time on link A with respect to the flow on link A is positive for every link A. Okay. Just that now the travel time is a function of not just the flow on that link, but also the flow on the opposite link here. Okay. And the other condition is that an additional flow unit in a given direction will affect the travel time in that direction more than it would affect the travel time in the opposite direction. Okay, this is a new condition that we had not seen before. Mathematically, it means that when you take the partial derivative of the travel time on link A with respect to the flow on link A, then that is larger than the travel time change that would happen with respect to so the same flow unit will be affecting more travel time in this direction as compared to the travel time in the opposite direction. Okay. So, this is what this condition means here. So, here we are taking the partial derivative with respect to the same flow x A here, but in the top we have the travel time of link A, and here we have the travel time of the opposite link here. Okay. So, it has been found that the actual link performance functions tend to satisfy both the conditions. Okay. So, using these two conditions, it can now be shown that the objective function is strictly convex, and therefore, since the constraint set is convex, because the constraint set is the same as the normal user equilibrium case when there are no link interactions. So, the constraint set is linear and therefore convex, and therefore, if you are able to argue that the objective function is strictly convex, then it is also convex everywhere and it is strictly convex at the stationary point also, and therefore, its minimum will be unique whatever you find. Okay. But that is applicable when these two conditions or these two assumptions hold that we just discussed. Okay. So, this we will be discussing in the next class, and with this we will be ending the lecture here. Thank you.